And then let's talk range. Whoa. What's the smallest y value? Now it's 0, right? And that's included in my range because there is a point on my graph that has a y value of 0, right? The only time you're going to have endpoints not included on graphs like this is when you actually have that open point. So if there's not an open point at that where 0 is, where the y value of 0 is, then that's definitely included. Even if there's not a big black dot there, it's still included. So we're including this guy. And then as we move up from that, so we see we have an arrow pointing up, so we know we're going to go to infinity, but we have to, again, figure out if there's any vertical gaps in between. So as we move up our graph from that point at the bottom, are there any y values that our graph doesn't hit between this arrow and this point? There's not, right? In fact, in this case, this piece right here accounts for every single y value between 0 and infinity. Like, there's some more points, or there's some more parts of the graph that touch some other y values in between, but having additional pieces of my graph doesn't take anything out of my range. So I've already accounted for all the y values between 0 and infinity just from that piece. And all these other pieces aren't going to take any of those y values out. So if I pick any y value between 0 and infinity, there's going to be some point on my graph with that y value. So again, we don't have any gaps in between. Okay, so you guys look at that next one and try to think about what that might look like as far as domain and range go. Oh, my coffee's going. I keep trying to drink it. Okay, what about my domain? What's my domain? You guys can say it out loud, it's okay. Negative infinity to infinity, yeah. So again, just like the graph before, or the function over here on the left, there's no smallest value, there's no largest value, and none of those jumps are horizontal jumps, right? None of those gaps cause me to skip any x values. What about my range? What do you think? So if I did this, could you tell me what my range was? What is it? Yeah, it just goes from 0 to infinity. I mean, it's essentially the same thing as the one we just did, right? So we know that we're going to go from 0 to infinity. But then we have to think about that piece down there. What y values does that piece contribute to my range? Just -3, right? So it's a lot like when we had this discrete graph over here where there's just one y value for each point. Well, it turns out that that piece down at the bottom, there's just one y value accounted for that whole piece. And so we're going to have to add on this little tiny discrete set.
Yeah, I saw that symbol in my math lab, and I couldn't figure out why I kept getting that question wrong.
The union? Yeah, so we talked about that yesterday. Where'd they go? When we were talking about those, like when we were looking at the number lines. Right? So if we have more than one set that makes up a domain or a range, then we just use the union to put them together into a single set. Because your domain and range are single sets, but they don't always connect to each other, right? So like if I have an interval and another point that make up my range, the union just says throw both of those in there, and that makes your entire set. And make sure you don't use, when you're typing it, make sure you don't use the U button, like the U key. It's not actually the letter U, it's the union symbol, and there's a button for it in MyMathLab, or you can type cup and it'll just appear. But yeah, I've had people use like the letter U, and then it doesn't read it the same way. Any questions on how we got there? So you're usually going to see this type of thing when there's a horizontal line that's disjoint from the rest of your graph, because that horizontal line just accounts for one y value, and then the rest of the graph accounts for a bunch of other y values, but they're not touching each other, right? So we can't say that we're going from -3 all the way up to infinity, because if you pick a y value between -3 and 0, there is no point on our graph that has that y value. So there's no way to use an interval to describe all of the y values on that graph, because there's like this separate little piece at the bottom. And you can, one thing you can do on these piecewise functions that have different pieces on them is you can say, okay, well, this piece is just the y value -3. And this piece goes from 0 to infinity. And then this piece goes from 1 to infinity. So you can describe each of them separately and then ask yourself if there's any overlap, right? Like this interval already includes all of those numbers, right? So if you talk about all the numbers that are greater than 0, you're already including all of the numbers that are greater than 1. And so that's why we end up not actually needing that piece when we express our range, because we've already included it in one of the other pieces. So you can list them all separately and then ask yourself if there's any overlap. So if you're already including one of those intervals in another one of them, then you don't need to write them both. That's just redundant, right? And so that's why we end up with just those two pieces, because that third piece is already taken care of by one of them. Just like over here, we could have listed all three of those separately, but 0 to infinity includes 3, which is what this gives us, and it includes everything greater than 2, which is what that piece gives us. So we can throw out pieces that we already have in one of them.
So what does the filled-in dot
Mm-hmm.
and NT mean on that one?
So the filled-in dot just tells us that the endpoint is included as opposed to not included. So like this endpoint, so those 2 points are endpoints of one of our pieces. And we fill one of them in to show that that's actually a point on our graph. So the ordered pair 2, 3 is an ordered pair that's part of that relation, right? So if you give me an input of 2, that gets you the output of 3. Whereas this point 2, 2 is not a point in my relation. So the input of 2 will never give me an output of 2. But we'll get infinitely close to it. And so we use that open point to show that we get infinitely close to that 2, 2, but we never actually get there. But the dark point says we're actually getting to the point 2, 3. So that's actually part of the relation. And they only do those big black dots at endpoints. So that's why like here, like this point at 0, 0, we don't have a big dot there, but it's included because everything on the curve is included, except those guys with the open points. Whoops.
So even if it doesn't have the fill-in dot,
Mm-hmm.
that means it's still counted for from 0 to infinity.
Yeah, so the curve itself is a whole bunch of those filled-in dots stuck infinitely close together. So it's an infinite number of those dots stuck infinitely close together. It's impossible for us to actually draw an infinite number of those dots, right? Which is why you don't actually see a filled-in point on any of the points on the curve except for at the very end. But that's what makes that curve or a line, is just taking an infinite number of those and sticking them infinitely close together. And so anywhere that the curve touches, you do have like a big black dot. It's just not, like, you can't see it because there's an infinite number of them close together. So yeah, I mean, that part's a little bit confusing. So in general, you just want to remember that the only time you're not going to include a point is if you have one of those open dots. So if, here's a good example. If this graph didn't include that piece and I had an open point right here, then I would say it's the range is 0 to infinity, not including the 0. Because that point at 0, 0 isn't part of my relation. So it's not actually an ordered pair relating an input and an output. It's just a place that I get close to.
So it jumps over
Right, so because that's still the lowest point on the graph, but because it's open now, it's not included. Okay. Whereas if it's not an open point, that 0, 0 is included. Other questions on these guys before we move on?
What if it was closed and it was a 0?
So what do you mean, like?
So like,
if I put like a dot right here?
Yeah, and then we.
So that's what's actually happening. Is there's a dot there? Do you mean like if this wasn't here?
Yeah, if that wasn't there.
That would still give me the same range, because everything in this portion, or all the y, I shouldn't say everything, all the y values in this portion of the graph are also accounted for by this portion of the graph. Right? Those two pieces hit the same y values. So whether this piece is here or not, I still hit those same y values. So that's kind of the tricky part of all of this, is you want to remember the range is just saying that if you pick any number in that set, there is some point on the graph that has that number as a y value. So there might be like 500 points on the graph that has that y value, but as long as there's one of them, then it's in the range. So, I mean, it would be ugly, but I could, my function could, well, that wouldn't be a function, but here's a good one. Like, if this went like this, I'm hitting those values between 0 and 1 a whole bunch of times with different x values, but the y values are still between 0 and 1. So if nothing else was on this graph, the range of that is 0 to 1, including both, whether it's drawn like that or whether it looks like this. Those two hit exactly the same y values, regardless of how many times it hits them. I don't know what I started with. There we go. Does that help? Okay. Other questions? Okay, so we've talked about domain and range graphically. Now we're going to talk about it algebraically. We won't do ranges algebraically in this class. Really, for the reason we were just talking about, like the range isn't super useful as far as how the function behaves, because it could look a whole bunch of different ways and hit the same y values. The domain is extremely useful with respect to how the function behaves, because we know for a single x value there can only be one point corresponding to it, whereas the same isn't true of y values, right? So the domain is really what we focus on mostly when we talk about the behavior of a function, because it tells us more specifically like what points are actually part of our function than the range does. The range is like, yeah, there might be 1,000,000 points with these y values, or there might be like 2. So when we talk algebraically, we're just going to find domains. And so when we're talking about finding domains algebraically, we're saying, okay, if I have the function like f of x equals 2x. When I ask what the domain of that function is, I'm asking what numbers can I multiply by 2 and get some sort of output that makes sense. So essentially, if you put it in your calculator, what number can I multiply by 2 and not get an error on my calculator? And really, when we're just multiplying by 2, we know we can do any number, right? You can multiply any positive number by 2, you can multiply any negative number by 2, and you can multiply 0 by 2. And no matter what, you're still going to get an output that has a numerical value. You're not going to get an error. So what we need to think about when we think about these guys algebraically is we have to ask ourselves, well, this rule over here on the right side, what operations is it performing on our input? And are there any numbers that I can't do those operations with? So we're going to start by listing. Whoa, don't look yet. Don't look. I give it away. We're going to start by listing all the possible operations we might see and thinking about what numbers we can do those operations with. And it's going to start out kind of boring because the most basic ones you can do with any number. And in reality, most functions are defined for all real numbers, which is kind of nice because, if you're just taking a shot in the dark, pick all real numbers and it's right some of the time, most of the time. So operations. So we have multiplication. Well, I don't want to start with multiplication. Start with addition. We have addition. So an example where we might see addition is like if you have the function f of x equals x plus 5. So the only operation in that function, remember, again, the rule on the right is it tells us what we're doing with our input to get our output. So this rule on the right says add 5 to your input. So what we want to know when we ask what the domain is what numbers can you add 5 to? And I usually break it down to like positive, negative, and 0, sort of are kind of the classes where I may or may not run into issues. So can I add 5 to positive numbers? Can I add 5 to a negative number? Can I add 5 to 0? Yeah, so no matter which one of those numbers you put in your calculator, adding 5 will always give you a numerical value as a result. You'll never get an error. And so we say that addition is defined for all real numbers. Which we abbreviate using this symbol. And I'll use that symbol so I don't have to keep writing all real numbers over and over and over again. So then what about subtraction? Whoops. So an example would be something like f of x equals x minus 5. So we want to think about if our function is subtracting 5 from our input, what numbers can I do that with? So can I subtract 5 from a negative number? Yeah, like negative 2 minus 5 is negative 7. Can I subtract 5 from a positive number? Can I subtract 5 from 0? Yeah, so addition and subtraction are just like moving up and down the number line, right? When you add a number, you move to the right, and when you subtract a number, you move to the left, which is possible all across the number line. And so this is also defined for all real numbers. So far, pretty boring. We can do any of these with any number. And then multiplication, we kind of already talked about. That's something like f of x equals 2x. And we can multiply any number by 2, right? You can multiply negatives by 2, you can multiply positives by 2, you can multiply 0 by 2. And getting an output of 0 is totally okay. Like, it might not be our favorite number, but it does have a numerical value. The value of 0 is still a number. It's not an error. It's not something that's undefined. So multiplying by 0 just gives us 0, but that's still a numerical output and still totally okay. So that is defined for all real numbers. Now, when we get to division, we have to be a little bit careful because there's sort of two directions you can do division in, right? You can talk about what numbers you can divide by another number, and then what numbers you can divide another number by. And so we're going to talk about division in two respects. First, we're going to say what numbers can we divide? So this is like the top of a fraction. So when I say f of x equals like x divided by 3, I'm asking myself, what numbers can I divide by 3? Can you divide a positive number by 3? Can you divide a negative number by 3? Can you divide 0 by 3? Yeah, you can, right? So remember, division is like, it's like the cookie situation, right? Where like, if you have 0 cookies and you have 3 friends, then each of your friends gets 0 cookies. And you might end up with 0 friends after that. But it's still a numerical value to say that I give each of my friends no cookies. And so this is, in this sense, division is also defined for all real numbers. Now, if we flip it, if we go the other direction, so division in the sense, what can we divide by? So this is something like f of x equals 3 divided by x. Can I divide 3 by a positive number? Sure, like 3 divided by 2, it's 1.5, right? Can I divide 3 by a negative number? Can I divide 3 by 0? No. That's one we can't do, right? Because if you have 3 cookies and you don't have any friends, it doesn't make sense to ask how many cookies each of my friends gets, right? You can think of it like the thing you're dividing by is like how many groups you're dividing into. So if you like have a single pizza and I give you a knife and say cut that into 0 pieces, that's impossible, right? I can't divide a whole pizza into 0 pieces because every time I cut it, I get more and more pieces. There is no way to make nothing out of a single pizza. So we cannot divide by 0. What's up? Oh. So you guys see the difference between the two? So in the second one, we're asking what numbers can be in the denominator of a fraction as opposed to what numbers can be in the numerator. So if we have a fraction in our function, denominator, then we can definitively say that the denominator of that fraction cannot be equal to 0. And that's the first restriction that we see on domains is if your function, if the definition of your function on the right side, if that rule involves division, so visually if we see a fraction, then we can say there's going to be a restriction on the domain. Any value that makes the denominator 0 is not going to be in my domain because if you were to plug that into your calculator, you would get an error. So like if you put 3 divided by 0 in your calculator, it spits out an error. You don't get a numerical value. And then after that, like these are sort of our 4 basic operations. After that, we think of things like exponents, but exponents are really just multiplication, right? If you have like x to the 5th, that's just x times x times x times x times, I lost count, but it's 5 factors of x being multiplied. So exponents are really just, they just represent more multiplication. And since multiplication is defined for all real numbers, something like x to the 5th is also defined for all real numbers. So we don't have to really worry about that separately. Square roots. I'm going to write even roots. So for now, you're only going to see square roots. You won't see other roots. But when we, I don't want to use that. Let's use 64. When we ask what the square root of 64 is, we're asking the question, what number do you raise to the 2nd power to get 64? So in this case, it's 16. When I say even roots, I'm talking about things like the 4th root, the 6th root, the 8th root, the 10th root. When we take the 4th root of 64, we're asking what number do you raise to the 4th power to get 64. If you take the 6th root, you're asking what number do you raise to the 6th power. So what we call the index of a root has to do with what exponent that root corresponds to. So what exponent you're like undoing. So in this case, the 4th root of 64 is 4, because if you raise 4 to the 4th power, I'm pretty sure it's 64, isn't it? Yeah. No, I'm sorry, it's 3. The 3rd root of, now I think this is 256. That's 4. If you raise 4 to the 4th power, I think you get 256, right? Yes. 2 times 2 times 2 times 2. The point being, the reason I'm saying even roots is that as we get into more complex radical functions, we will see roots other than the square root. Right now, you will not see roots other than the square root, but that's why I'm generalizing and saying even roots instead of just the square root, because everything we say about square roots also applies to the 4th root and the 6th root and the 8th root and the 10th root. And if you don't quite understand what those are at this point, that's totally fine. We'll cover them in more detail, but that's why I'm generalizing here and not just saying square root, because there's other roots. So let's look at one that just has a square root in it. F of x equals the square root of x. So this function is taking the square root of the input. Can you take the square root of positive numbers? Can you take the square root of 0? Yeah, the square root of 0 is just 0. In fact, any root of 0 is just 0, because if you raise 0, like no matter how many times you multiply 0 by itself, you get 0. What about negative numbers? Can you take the square root of a negative number? I mean, we can if we're talking complex numbers, but this class is all about real valued functions, so we're not worrying about complex numbers. The reason we can't take the square root of a negative is that when you take the square root of a number, you're asking what number can you multiply by itself to get this number under the square root. And if you multiply a negative number by a negative number, so by itself, you get a positive. And if you multiply a positive number by itself, you also get a positive. So there is no number that you can multiply by itself to get a negative. And therefore, there's no answer to the square root of a negative number. So we can't take the square root of negative numbers. So what that means in terms of finding the domain is whatever it is we're taking the square root of, in this case it's just x, this piece right here we call the radicand. So if we have a function that involves a square root, then we can say that the radicand, whatever it is that's inside that square root, has to be greater than or equal to 0. So greater than 0 means it's positive, equal to 0 means it's 0. So that accounts for everything that's not negative, right? If it's greater than or equal to 0, it's just not negative. And then the last thing we'll talk about is odd roots. An odd root is something like the cube root. So when we take the cube root of a number, we're asking ourselves, what number do you raise to the 3rd power to get that radicand? So, for instance, the cube root of 8 is 2, because 2 to the 3rd power is 8. Can I take the cube root of a negative? For instance, how about negative 8? Is there a number you can multiply by itself 3 times to get negative 8? Yeah, negative 2 times negative 2 times negative 2 is negative 8, right? So the reason this works is because when you multiply a negative number, when you multiply 3 factors of a negative number, you get a negative number. So if I raise a negative number to the 3rd power, I can get a negative number. Whereas if I raise a negative number to the 2nd power, I will always get a positive. So that's why odd roots and even roots behave differently, because raising a negative or multiplying an odd number of negative factors does give you a negative number, whereas multiplying an even number of negative factors is going to give you a positive, because those pairs always create a positive. And so this odd roots are defined for all real numbers. So you have to be a little bit careful. Just because you see a radical symbol doesn't necessarily mean that you have to treat it like a square root. You want to look at what this number is up here. We call that the index. And if you have a little odd number right there in the little crook of your radical, then it's an odd root. And those are defined for all real numbers. You don't have to worry about any restrictions on your domain. So let us now do a crap load of examples. But don't look, I thought I deleted all this. Okay, so let's start with, here, oops. Find the domain. Okay, so f of x equals 1 over x minus 5. So when it comes to finding the domain, when you're given a formula for your function, what you want to do is you want to look at that rule on the right side and ask yourself what operations are involved. So what operations do you see here? There's division and subtraction. So fractions always represent division, and that's usually how we see them, rather than like a divided by sign. So we have division and we have subtraction. Well, subtraction I have no problem with. I can do that with any number I want. But division poses a problem, right? We can't divide by 0. And so that's where we come back to this statement that the denominator of any fraction can't be 0. So we're going to say x minus 5. So just the denominator cannot be 0. And we use that little slash to show that it's something that's not in the domain as opposed to what is in the domain. Because as we work with more complex functions, it can get a little confusing if you're finding what is in the domain or what's not in the domain. So, but we treat that just like an equation. So we solve that just like we would solve the equation x minus 5 equals 0. We add 5 to both sides. And that tells us that x cannot be 5. Because if I put 5 into this function, the first thing I would do is do 5 minus 5 in the denominator, right? And that would give me 0 down there. And then all of a sudden that gives me an error. And so what's this look like on a number line? Well, if x cannot be 5, then it can be anything less than 5, but not including 5. And it can be anything greater than 5, also not including 5. So we saw an example like this yesterday at the very beginning of class when we were talking about like the different sets, right? So I have 2 intervals here, but there's no way to get from one to the other without jumping over the number 5. So that's going to give me 2 intervals with a union. So everything less than 5, everything greater than 5, and then I make a single set out of those just by putting in union. So far, so good? So what this is saying is that if I choose any number that is less than 5, or if I choose any number that's greater than 5, and I plug that into that function like on my calculator, it's going to spit out some number. It might be an ugly decimal, but I'm not going to get an error. Whereas if I plug 5 in there and I punch that into my calculator, I will get an error because this function's not defined. It doesn't make sense for an input of 5. It's kind of like when we were talking the first day about functions, when we had like the very first example of relation we had was that you're going to pair people with the dorm they live in, right? And we said, well, that doesn't make sense to even ask the question, what dorm do you live in, to somebody who lives off campus, right? If somebody lives off campus, then it doesn't make sense to ask them what dorm they live in. And so the students that live off campus weren't part of our domain because the function didn't make sense. The question didn't make sense if I asked it of somebody who didn't live on campus. So in our example there, our domain was just the students that lived on campus. It wasn't all students. So the same is true here. Doing that division doesn't make sense if the denominator is 5 minus 5. And so I have to take 5 out of my domain because the operations that this function defines are just don't make sense if I use an x value of 5. And so that's what we're doing when we find our domain is we're asking ourselves what numbers do these operations make sense for? Let's do... Okay, so what operations do you see? Addition, multiplication, and a square root. So we're totally fine with addition and multiplication, right? We can do that with any number we want. But when we see that square root, we remember that you can't take the square root of a negative. So whatever it is that is inside the square root, this whole expression right here is what we're trying to take the square root of. And so that whole expression can't be negative. So that's what we call our radicand. And that has to be either greater than 0 or it has to be equal to 0. Which means our domain is made up of x values that make that statement true. That make whatever it is we're taking the square root of greater than or equal to 0. So I can solve that. This is like the sole reason that we covered solving inequalities last week. Yes?
Will that always be greater than or equal to 0? Or?
Yes. So the radicand always... The only thing that we can't take the square root of is a negative. So whatever is inside that radical has to be greater than or equal to 0 because it has to be positive or it has to be equal to 0.
There's a negative there.
A negative where?
In the radical.
So like if I had a minus 12,
Yeah.
the same would be true.
Okay.
So like that 3x plus 12 or 3x minus 12 or whatever it happens to be represents just some number. And whatever that number is has to be greater than or equal to 0 because that's the number I'm going to end up taking the square root of after I do the multiplication and the addition. So I'm going to solve this guy. 3x is greater than or equal to negative 4, which means that, whoa, sorry, I'm getting ahead of myself, is greater than or equal to negative 12, which means that x is greater than or equal to negative 4. And so it's totally fine for x to be some negative numbers. Like x can be negative 1, because if I take negative 1 and I multiply it by negative 3, I get negative 3. But then adding 12 to that gives me a positive number. So if you think about this in terms of order of operations, there's some negative numbers I can put in there because before I take the square root, I will end up with a positive. Right? So after I multiply negative 1 by 3 and add 12 to it, that gives me a positive number before I try to take the square root of it. So it's not that x can't be a negative number. It's that whatever that whole thing is under the square root, that can't be a negative number. Because in this case, order of operations would have us taking the square root last. So I have to do all that addition and multiplication and whatever is under there first, and the resulting number has to be positive or 0. And so my domain here is everything oops, I'm going the wrong way. Everything that is equal to negative 4 or greater than negative 4. So negative 4 to infinity. So probably the trickiest part of this whole thing is that everything is based on the operations in the function. So it has nothing to do with what your function looks like or what your resulting domain is going to look like. You have to take all these operations like one at a time. So if I have g of x equals, let's say, the square root of x minus 6 divided by x plus 1. When I list my operations, I see addition, subtraction, division, and a square root. That means I have to do what I did in these first two examples separately. I have to deal with the fact that there's division, and I have to deal with the fact that there's a square root, and then I'll combine those to get my domain. So, which one do I want to do first? I'll do this one first. The fact that there's a square root, what am I taking the square root of here? What's inside that? Just x minus 6, right? That's the only number that I'm taking the square root of. So x minus 6 has to be greater than or equal to 0, which means that x has to be greater than or equal to 6. So that gets me this set. Damn it. I don't have time to do another one, so let's scrap this. I'm sorry. I mean, we could do this just fine. It would just be really boring. There. Sorry. My bad. There's nothing wrong with the function I wrote the first time. It just doesn't illustrate the point I'm trying to make. So did everybody make that change? The denominator is x minus 1. The numerator is the square root of x plus 6. And so far, we have that whatever x value we put into this function has to be greater than or equal to negative 6. But then I say, oh my goodness, I have division too. That's what I do when I'm doing math at home. I say, oh my goodness, all the time. There's also division going on here, right? And so the thing that I'm dividing by, which is x minus 1, well, that can't be 0. And that's true completely separately of what's going on in the numerator and what's going on with the square root. I can't divide by 0 no matter what's in the numerator. And so if x minus 1 can't be 0, that means that x cannot be 1. So I already decided that x has to be greater than or equal to 6, or negative 6. But on top of that, I'm now going to say, well, I need like a hole here. So I can be any number that's greater than or equal to negative 6, except for positive 1. So you want to think of these as you're starting with all real numbers, and then the square root narrows it down, and then the division narrows it down some more. So you're sort of like plucking things out of your domain as you go to satisfy the restrictions on each operation. So we have to satisfy the restriction because of the square root, and then in addition to that, satisfy the restriction caused by the division. So we kind of started with a bigger set, narrowed it down a bit, and then we're narrowing it down some more. So I can be anything between negative 6 and 1, and I can be anything greater than 1. So my domain is going to be negative 6 to 1, and then 1 to infinity. So as you do these, what I want you to remember is all of this is based on the operations that are going on, and no matter how I configure the operations, you'll address the square root, you'll address the division, maybe separately, and then put all those restrictions together to get your domain. So the problems that you do aren't necessarily going to look just like this, right? But they are going to contain only those operations. So if you think about it all in terms of the operations you're trying to do and what the restrictions on the individual operations are, you can make this function like all sorts of confusing. You can be like a square root plus 72,000x divided by like all this other stuff. But if you look at the operations individually, you can put it all together to get a domain, no matter what your overall function looks like. So